Hello all, welcome to the video series on SIPI by E for Engineer. In the last videos, we have discussed the four categories into which the signal integrity problems fall into, and we have also discussed the signal quality of a net and the crosstalk. In this video, let us focus on the remaining categories, which are rail collapse and EMI. So, what is a rail collapse? When the currents through the power and ground path changes as and when the chip switches its outputs or core gates a switch, there will be voltage drop across the impedance of the power and ground paths. This voltage drop will mean less voltage gets to the chip, which will see a decrease or collapse of the voltage between the power and ground rails. In high performance processors, the trend is for lower and lower power supply voltages or drive voltages, but higher power consumption. This means higher currents will be switching in short amount of time, and the amount of noise that can be tolerated will decrease. So if the chip has higher drive voltages like 5 volts, 3.3 volts, then the noise the chip can tolerate will be high. But in recent days, that is like for high performance processors, the trend is that they are using some zero point 0.8 volts or zero point 0.7 volts of drive voltages, and because of this, the noise margins the chip can handle is also decreasing. As the drive voltage is decreasing and the currents are increasing, any voltage drop associated with the rail collapse is becoming a bigger and bigger problem. So that is why, to mitigate this problem of rail collapse or voltage drop, the goal should be we should design the impedance of the power and ground networks as minimum as possible. To achieve that, there are some ways, and the first way is to use thin dielectric material between the power and ground planes. This will be taken care when we get a technology from foundry itself, because the foundry recently what it's doing is it is trying to use very thin dielectrics in between the power and the ground planes, so that it will help us in designing low impedance PDNs. And the second important thing is to use decoupling capacitors. These decoupling capacitors we can put on the die or on the package or on the PCBs. So what these decoupling capacitors will do is, when there is high switching activity in the chip, for that particular amount of time there will be huge current demand, and during that time there will be drop in the voltage. So these decoupling capacitors, what they will do is they will try to stabilize the voltage for some time until it is drawn from the supply voltage. So these are the ways how we can mitigate the rail collapse noise. And now let us focus on EMI. EMI is nothing but it is radiation from all electronic devices. Like we'll be hearing that we will be observing radiation from phones, PCs, or any other electronic gadgets. So all these things we call it as EMI. And now in this, we will see the EMI with respect to boards or PCBs. So with board level clock frequencies in the 100 to 500 megahertz range, or simply in megahertz range, the first few harmonics are within the common communication bands like TV, FM radio, cell phone, etc. This means there is very real possibility of electronic products interfering with our communication until and unless the electromagnetic radiations are kept below acceptable levels. So, how an EMI problem arises? So, it takes three things for an EMI issue to rise: the source of the noise, and the antenna which radiates the noise, and a pathway to the radiator. In addition to these things, every source which causes SI problems is a source of EMI problems as well. And most of the EMI radiations arise from PG networks as well. So, to mitigate these EMI issues, if we take care of the SI issues and the PG issues, these EMI issues will be automatically taken care. So that's all for this video. So with this video, we have finished discussing all the four categories of the SI problems, and in future videos we will discuss more on SI and PI. Until then, stay tuned and subscribe to E for Engineer. If you have any doubts, please visit www.logicissoc.com or mention in the comment section. Thank you so much.